The two main topics of Chapter 8 are exponential functions and logarithmic functions. And so as you can see, there are 7 topics we'll be covering: exponential functions, composite functions, and inverse functions, then logarithmic functions, and then the properties of these logarithmic functions. And we talk about natural logarithmic functions, and then we cover solving exponential equations and logarithmic equations, and finally we do some mathematical modeling with exponential and logarithmic functions. So let's start with section 8.1, where we have the following topics. We're going to graph exponential equations and functions, and then we graph these exponential equations in which x and y have been interchanged, and then we solve some applied applications and problems with exponential functions and their graphs. And as usual, we begin our discussion with definitions. And so here's the definition of an exponential function. The function f of x equals a to the x, where a is a positive constant different from 1, is called an exponential function base a. And the following are examples of exponential functions: f of x equals 2 to the x, f of x equals 1/2 to the x power, and f of x equals 0.4 to the x power. Notice that in this description of the function, the 1/2 is in parentheses. This is really important to note. So note that in contrast to polynomial functions like f of x equals x squared and f of x equals x to the third, the variable here is the exponent. So let's consider some graphs of exponential functions. So notice the difference is f of x equals a to the x versus the polynomial f of x equals x to the third or x to the second power. For example, to graph f of x equals 3 to the x, we complete the table, and these will be our ordered pairs. Then we plot the points from the table and connect them with a smooth curve. So this means we replace x with 0, and 3 to the 0 power, of course, is 1. So f of x equals f of 0 equals 1. And when x equals 1, f of 1 equals 3 to the 1, or equal to 3. When x equals 2, then f of 2 is equal to 3x to the second power, or 9. And f of 3, when x equals 3, we have 3 to the third power, and that's equal to 27. And when x is equal to -1, so f of -1 is equal to 3 to the -1, which of course is 1 divided by 3 to the first power, or simply 1 divided by 3. So it's equal to 1/3. And when x equals -2, f of -2 equals 3 to the second power, or 1 divided by 3 to the second power, or 1 divided by 9, so 1/9. And when x equals -3, then we have f of -3 is equal to 3 to the -3rd power, or 1 divided by 3 to the 3rd power, which equals 1 divided by 27. So that's 1/27. So we have these ordered pairs. Let's plot them. So we plotted the points and connected them with a smooth curve, and this is what f of x equals 3 to the x looks like in terms of a graph. In a similar way, to graph the function f of x equals 1/3 to the x power, we complete the table, and then we plot the points from the table, and again connect them with a smooth curve. So when we choose the values for x, f of 0 is equal to 1/3 to the 0 power, and that is of course is equal to 1. So here we've evaluated the function f of 0, equal to 1. F of 1 equals 1 to 1/3 to the first power, or 1/3. F of 2 means 1/3 to the second power, or 1/9. F of 3 would be 1/3 to the third power, or 1/27. When x equals -1, we have 1/3 to the -1 power, which means 1 divided by 1/3, which is 3. And when x equals -2, then 1/3 to the -2nd power is 1 divided by 1/3 to the second power, which is 9. And when x equals -3, then 1/3 to the -3rd power is 1 divided by 1/3 to the third power, or 27. So here we have our ordered pair 0, 1, 1, 1/3, 2, 1/9, 3, 1/27, -1, 3, -2, 9, and -3, 27. And then we plot these points. Here we plotted the points. And here's the graph. The graph of f of x equals 1/3 to the x power. Here's an important observation about the y-intercept of an exponential function, and that is all functions of the form f of x equals a to the x goes to the point 0, 1. That is, the y-intercept is 0, 1. For exercise 5, we are asked to graph the function f of x equals 2 to the x plus 2. So we create a table of values, plot the points, and then connect the points with a smooth curve. And so here is the graph of the function f of x equals 2 to the x plus 2. In exercise 6, we are asked to plot the graph f of x equals 2 to the x minus 4. And so we have a table of values here for x. We will compute the corresponding functional values. And then we have the ordered pair, which we will plot on the graph, and then connect the dots with a smooth line. Here we've evaluated the function for x equals 0, 1, 2, 3, and 4, and x equals -1 and -2. And here are the corresponding function values. So we've got the ordered pair 0, -3, 1, -2, 2, 0, 3, 4, 4, 12, -1, -7/2, -2, -15/4. Now we're going to plot the points and then connect them with a smooth curve. So here's the graph of f of x equals 2 to the x minus 4. Next, we will be looking at equations with x and y interchanged. For example, when we look at number 7, graph x equals 3 to the y, it was in the previous, or similar to previous examples, y equals 3 to the x. But now we exchange x and y, and so we do the same thing. We create a table of values, and then we plot the points, and then we create the graph. Here's a table of values where we chose some values for y, and then computed the corresponding value for x. And here are ordered pairs 1, 0, 3, 1, 9, 2, 1/3, -1, and 1/9, -2. So let's plot these points and then connect them with a smooth curve. And here's the graph of x equals 3 to the y power. Next, we'll be looking at some applications of exponential functions, and one of the more basic ones is the interest compounded annually. And so the first problem asks us to find the amount in an account after 1 year and after 2 years if $40,000 is invested at 2% compounded annually. So it begins with the consideration that after 1 year, the amount is 40,000 plus 40,000 times 2%, or times 0.02. And so when we factor out the 40,000, we get 40,000 times 1 plus 0.02, and that is equal to 40,000 times 1.02. And that is equal to $40,800. $40,800. Then the amount after 2 years is then now 40,800 plus 40,800 times 0.02. And as before, we factor out now 40,800, and then we add 1 plus 0.2, and that gives us 40,800 times 1.02, and that is equal to $41,616. So that's how we can compute compound interest, given that the compounding takes place once a year or annually. Here's the formula when interest is compounded annually. So the amount of money A that a principal P will grow to after T number of years at interest rate R, written in decimal format, compounded annually, is given by the formula A equals P times 1 plus R, parentheses, to the power of T. In the next exercise, we consider the interest compounded annually for an amount that's of 40,000 that's invested at 5% interest. It's compounded annually. So there are 3 parts to this. A, find a function for the amount in the account after T years. Find the amount of money in the account at T equals 0, T equals 4, T equals 8, and T equals 10, and then it graphs a function. So remembering that the general formula is equal to A equals P times 1 plus R to the T power, then in this case we have A of T equals 40,000 and since the interest rate is 5, 1 plus R, 1 plus 0.05 would be 1.05, 1.05 to the T power. So that's the answer for A. Then for the B part, that means we evaluate A of 0, A of 4, A of 8, and A of 10. So when T is equal to 0, then the whole exponent, this part will be equal to 1, and so the amount will be 40,000. A of 1 is equal to 40,000 times 1.05, and that's 48,620.25. And then, A of 4, pardon me. And then A of 8 is equal to 59,098.22, and A of 10 is equal to 65,155.79. So when we make a table of values and graph the functions, then it's going to look like this. On the horizontal axis, we have the number of years as usual, t being the independent variable. So 2, 4, 6, 8, 10 years. And then on the vertical axis, we have the amount a. And so here's a function a of t equals 40,000 times 1.05 to the t power. And so this curves only very slightly. And the reason for it is that the difference between 1.05 and 1 isn't all that great. If it was equal to 1, of course, it would be a straight line. And so the larger the base is, the more quickly the function will rise. So here it rises very slowly, but considering that after 10 years you've got over $15,000 in interest, that's actually pretty good. But again, this graph only has a very slight curve. Now next is the compound interest formula, or it's an exponential function. If a principal P has been invested in an interest rate R compounded n times per year, so n is the number of times it's compounded per year, and in t years it will grow to an amount A given by this expression. A equals P times 1 plus R divided by n to the n times t power. So here the exponent is n times t. I hope you can read it, but that's really what it is. N times t, the product of the number of times it's compounded per year times the number of years. Here's an example of a guided solution. A couple invests $7,000 in an account paying 3.4% compounded quarterly. Find the amount in the account after 5.5 years. A couple of observations. It would be a real good idea to write down what P is. So P is equal to 7,000. R is equal to 3.4%. or 0.034. And t is equal to 5.5 years. It would be 11.5 years. And n, since it's compounded quarterly, it means n equals 4. So then, filling in the blanks, 3.4% divided by 4, and then n times t would be 4 times 11 divided by 2, since t is equal to 11 divided by 2 years, 11.5 years. And so it would be 1 plus 0.034 divided by 4 to the, now 2 against the 4 makes it a 2, and 2 times 11 is 22, so it would be 22nd power. And so that would be, in parentheses now, we divide 0.034 by 4 and add it to 1, and that's equal to 1.0085. So we raise that to the 22nd power, and I hope you have discovered in your scientific calculator how to do that. So again, order of operations indicates that we do the expression parentheses first and then multiply it by 7,000. And by doing that, the amount A will be approximately equal to, rounding it to cents, to 2 decimals, would be $8,432, $432.72. So that's how the compound formula works. And this is the end of section 8.1.